on Race to Save the Planet, the biggest threat to the world's environment, climate change. Already, man-made gases are destroying the ozone layer. Now, more gases may bring greenhouse warming.
It took 10,000 years to warm the planet up only 5 degrees Celsius, about 9 degrees Fahrenheit, and we're talking now about change on that magnitude in a century.
The consequences could be devastating. How likely are they? What can we do about it? After all, we have only one atmosphere.
Major funding for Race to Save the Planet is provided by the Annenberg CPB Project and public television viewers. Corporate funding is provided by Ocean Spray. Our continuing aim is to preserve and protect what we cannot create. Additional funding is provided by Jessie Smith Noyes Foundation, Corporation for Public Broadcasting, the John D. and Catherine T. MacArthur Foundation, and Carnegie Corporation of New York, and by the following.
The greenhouse effect, the hole in the ozone layer. You may have wondered what exactly these things are. In this episode of Race to Save the Planet, we're going to show you. And no, you don't have to be a science professor to get it. And yes, it is important. Why? Because we're conducting a giant experiment on the only atmosphere we've got. And right now, we don't know the outcome. So we'd all better know exactly what's at stake. Quite a few people don't believe that mankind is capable of damaging anything as huge as the world's atmosphere. If you're one of them, you're going to be especially interested in the first story in this film about ozone destruction and the consequences for the people of southern Australia.
What I had was just a freckle, which is here, and it changed shape over time, and that made me suspicious that it could be something that wasn't normal. So I went to the doctor and asked to be referred to see a specialist, and from there it just went on, and within a week I was in hospital having major surgery.
Renata Meissen's surgeon was Dr. John Anstey, an expert in treating malignant melanoma, the deadliest form of skin cancer. Today he's looking for signs of a recurrence.
How you doing?
Good, thank you.
To give Renata the best chances for survival, Anstey had to remove almost half her cheek.
I remember now. Just about here.
Yep, that's right.
2 years later, she seems to be cured, but the scars will be with her for the rest of her life. Odds are Alan Lynch, another melanoma patient, won't be as lucky. 85% of these cancers are fatal, and it all starts with a little spot like this. While skin cancer is a global problem, what's unusual about Australia is the number of people getting it.
One after the other. We've really got an epidemic on our hands in this country. The incidence of melanoma is increasing alarmingly. We also have a very high incidence of other forms of skin cancer, to the point where 2 out of every 3 Australians before the age of 70 will have some form of skin cancer.
More than twice the world average, this high cancer rate is usually explained by Australians' love of the outdoors. Exposure to the sun's ultraviolet radiation causes skin cancer. And because the majority of people here are very light-skinned, they're especially susceptible to the sunburns that lead to this disease. But in December of 1987, the beginning of Australia's summer, something happened to make a bad situation even worse. Although the crowds of beachgoers weren't aware of it at the time, ultraviolet radiation from the sun began hitting them with unheard-of strength. It took about a year before the origin of this silent peril was understood, and the news came as a shock. It was people, not nature, that were to blame. The explanation begins 8 miles above Australia's beaches, where ozone gas is concentrated in a thin layer, which in fact covers the entire Earth. Ozone performs a vital function, blocking out the sun's dangerous ultraviolet light. But for the last 50 years, this ozone shield has been under attack by 2 kinds of man-made chemicals. Halons, used in some kinds of fire extinguishers, and chlorofluorocarbons, or CFCs. CFCs are used extensively as coolants in refrigerators and air conditioners, as solvents for manufacturing microelectronic chips, as blowing agents for making plastic foam. And outside Europe and America, CFCs are still used for pressurizing aerosol cans. These complex chemicals were designed to be harmless to humans who might breathe them at ground level. But once released into the air, they drift high up into the atmosphere where they break down into basic parts like chlorine and bromine. And these, it turns out, are efficient destroyers of ozone. Ozone gas is very unstable. It reacts easily with chlorine or bromine, forming new gases which no longer block the sun's ultraviolet light. Because of the limited quantities of chlorine and bromine in the air, it was first assumed only a small amount of ozone could be destroyed this way. But then came a big surprise. Antarctica, the coldest place on Earth. Every winter here, high in the atmosphere over the continent, there forms a frigid swirling mass of air called the winter vortex. In 1985, measurements inside the vortex revealed 40% of the ozone was missing. The now infamous ozone hole had been discovered. And with this finding, scientists realized that the destruction of ozone speeds up under very cold conditions. The immediate concern was for wildlife under the ozone hole. Everything from whales to microscopic plankton, which were now being exposed to dangerously high doses of ultraviolet radiation. But there was also a nagging fear. Could the ozone-depleted air drift someplace else? On December 11th, 1987, everyone's worst fears came true.
This is National 9 News with Brian Naylor.
Hundreds of rail workers...
The story didn't make the evening news that day. It took a while for the significance to sink in. But as TV weatherman Rob Gale showed us one night after a broadcast, what went on over the South Pole is now perfectly clear.
The problem began when a high-altitude air mass drifted from over Antarctica towards Australia. In wintertime, the circulation in the stratosphere over Antarctica, the air moves around in a fairly tight circle. But then in springtime, when the air becomes a little bit warmer, that circulation pattern breaks down. Now, in the spring of 1987, that breakup possibly looks something like this, with firstly a teardrop shape forming, becoming even more elongated until the stage where we had 2 distinct lobes, one of which then moved right over southern Australia, and it stayed there for almost a month.
Gotta go.
Weather instruments monitoring the atmosphere at the time did pick up a sudden ozone drop. It was not as severe as Antarctica, but Australian meteorologists realized there was a serious problem. Roger Atkinson.
In the 2 days between the 11th and the 13th of December, values dropped about 12% and stayed low for the rest of the month. That resulted in us getting the lowest December mean on record.
No, bony fingers in the neck.
While it's too soon to see any rise in cancer as a result of this incident, one thing is clear. More malignant skin cancers are inevitable if an ozone hole keeps drifting over the country in the future.
It's ultraviolet dependent, that is, the more ultraviolet, the more skin malignancy there'll be. Anything that produces more ultraviolet is, I think, going to add to our burden of skin malignancy in the community. If it's true that the depletion of the ozone layer increases levels of ultraviolet, then it becomes a matter of some urgency to do something about it.
Urgent at least for Australians, who have now experienced at least one episode of unnaturally high ultraviolet radiation. But could this happen to people in other parts of the globe? The The main place to worry about is the world's other very cold place, the Arctic. If a large ozone hole ever develops here, it will only have to drift a short distance before it covers densely populated areas of North America and Europe. To find out if an ozone hole could develop in the Arctic, an international scientific mission was put together in January 1989, sponsored by the U.S. space agency NASA. Scientists from 7 nations participated in this marathon analysis of the Arctic's upper atmosphere. And by the end of a month-long mission, their findings were startling. The cold winter conditions here were creating the same unexpected chemical reactions that speeded up ozone destruction over Antarctica. While so far only 7% of the ozone was missing, the scientists agreed the problem could get much worse if the world continues releasing CFCs. Clearly, Australians weren't the only ones at risk. Overseeing the Arctic mission was NASA's Dr. Robert Watson.
So while we haven't yet seen a large, massive depletion of ozone in the Arctic region, the fact that there is the potential for large-scale ozone depletion, I do believe, has got the attention of policymakers worldwide.
Major changes in the chemistry of the Earth's atmosphere are taking place, with potentially calamitous effects for all mankind.
Shortly after the Arctic mission, representatives of more than 80 nations met at international ozone conferences.
Which protects life.
40 richer countries pledged to eliminate all CFC production by the year 2000, confident that substitute chemicals will be available by then. But many poorer countries refuse to make that commitment because the substitutes are expected to be more expensive. Then, at a later conference, economic aid to help pay for substitutes was negotiated.
Thank you for coming.
The result? 100 countries now agree the atmosphere is being threatened by pollution. Unprecedented unanimity for an environmental issue, and an important step towards solving the problem.
Fortunately, we believe there's a solution to the ozone depletion problem. The problem's caused by a handful of man-made chemicals, and industry is working very actively to come up with environmentally safe substitutes. However, even if we solve the ozone depletion problem, that will not stop man's assault on the environment. Every day, we put numerous chemicals into the Earth's atmosphere that could have much more severe environmental consequences than that of ozone depletion.
In the summer of 1988, the world may have gotten a frightening preview of some of these severe consequences. Thousands of fires raged out of control in America's forests. Hurricane Gilbert hit the Caribbean with abnormal ferocity. Floods killed tens of thousands in Bangladesh. Record-high temperatures were registered in Beijing. And prolonged drought destroyed vital grain crops in the U.S. Midwest. Such unusual weather could become typical in the decades ahead if the world gets warmer due to the greenhouse effect. And our own pollution of the atmosphere will be to blame. The number one offender, carbon dioxide, a byproduct of burning coal, oil, and gas to power our energy-intensive world. In developing nations that are clearing land, large amounts of carbon dioxide also come from intentional burning of forests. The number 2 greenhouse gas, CFCs, the same gases which destroy ozone in the upper atmosphere. The number 3 contributor, methane. It leaks out of coal mines. It comes from more and more cattle, which produce the gas during digestion. And it comes from rice paddies, which create vast amounts of methane in their flooded soil. The way these gases raise the Earth's temperature is no more mysterious than what happens inside a car left parked in the sun. Solar energy comes in through the car windows in the form of light. Some of it gets converted to heat when it's absorbed by objects inside. But this heat has difficulty getting back out through the glass, so the temperature rises. Greenhouse gases do much the same thing as the car windows. They let sunlight in, but keep the heat from getting out. Not that greenhouse gases are all bad. Without some of them, the Earth would be freezing. Like Mars, where the thin atmosphere lets almost all the heat from the sun escape back into space. In contrast, the planet Venus has so many greenhouse gases, its surface temperature exceeds 800 degrees. While there's no worry the Earth will ever get that bad, over the past 2 centuries, the amount of one greenhouse gas, carbon dioxide, has increased by nearly 25%. And since 1880, when reliable records began, the world's average temperature has gradually increased by about 1 degree Fahrenheit. This warming is still too small to be certain it was caused by the increase in carbon dioxide, because some temperature fluctuation can also be natural. But the long-term outlook is obvious to climatologist Steve Schneider.
Right now, the Earth is like a car with the window rolled halfway down. There's a medium amount of greenhouse gases out there, and there's a moderate amount of heat that can escape. But if we continue to do things like burn fossil fuels and use cars like this, that's adding greenhouse gases to the atmosphere, which is like rolling the window up, keeping the car warmer inside. If we add methane and chlorofluorocarbons, that's rolling the window up some more, trapping more heat inside the Earth, warming the planet.
The big unknowns, says Schneider, are exactly how fast and by how much the temperature might go up, and what could be the consequences for the Earth.
So that
Using computers to simulate the Earth's climate is the only way to tackle these questions.
red because that's the CO2 doubled world.
It's a task requiring giant supercomputers, something fewer than a dozen climate research centers in the world have. Without these machines, no climatologist could grasp the jigsaw puzzle of factors which control our planet's climate. Running inside these computers are complex programs which attempt to calculate future climate by considering each piece of the climate puzzle. First, there's the sun, the energy source for the system. Then there's the atmosphere, including greenhouse gases and clouds. The vast oceans affect climate in many ways. And finally, there are different land surfaces. Some reflect sunlight, some absorb it. To make calculations manageable, computer climate models, as they're called, have to take a crude representation of the world and divide it up into large grid squares. Turning on the sun starts a simulation. Near the equator, sunlight is absorbed at the surface and converted into heat, warming the air above. The more carbon dioxide in the atmosphere, the less heat escapes back into space. Near the poles, the shallow angle of the sun and the fact that ice reflects sunlight both help keep the air above cool. These differences in air temperature create wind. Wind and heat together evaporate water from the ocean, which forms clouds and rain. So the computer can calculate all the conditions, temperature, wind, rainfall, which make up climate. A typical calculation predicts conditions in the year 2050, when carbon dioxide levels may have doubled, and conditions could be bleak, according to pioneering climate modeler Suki Manabe from the National Oceanic and Atmospheric Administration, and Warren Washington of the National Center for Atmospheric Research.
Our climate model essentially shows a warming in the tropics of 2 to 4 degrees, up to 6 degrees over the continental areas, and over the areas of sea ice, and we're getting even larger changes up to 10, 12 degrees.
When climate gets warmer, then over entire globe as a whole, there will be much more evaporation, but also there will be much more precipitation. And it may increase as much as 10%. And some place will become drier, other place may become wetter.
We're finding that over the Soviet Union, it is wetter at all times of the year. Over the North America, it is somewhat drier in the summertime. And the areas of Africa, China, and Brazil, it is drier all times of the year.
In summertime, there is what you call Indian monsoon phenomenon. The warm, moist air coming from south. This monsoonal precipitation may increase very substantially.
What's more, storms of all kinds are calculated to become more intense. Sea levels will rise, causing flooding in virtually every country with a coastline. And huge tracts of forest could die out as heat and rainfall patterns shift in a mere 50 years.
This magnitude of change in the climate system is huge, and I think there should be a lot of concern about whether society can adapt to this large of a change over such a short period of time.
Before we take a closer look at these dire predictions, first, why should we believe them? After all, they're just based on computer simulations. If we waited 50 years, of course, we could know for sure if the predictions were valid. Yet by then, it could be too late to turn around the problem. There is one way, however, to test the validity of the computer models today, by seeing if they can predict the past. Djibouti, Africa, a tiny desert nation where most people live a harsh nomadic life. The casual observer would assume Djiboutians have lived this way forever, but the casual observer would be wrong. Located just east of the Sahara Desert, the country today is nearly bone dry. About the only sign of water is this shallow, salty lake at a low point in the terrain, at the bottom of a big geological basin. But about 30 miles away, 200 feet higher than the shallow lake, there's striking evidence that yesterday's Djiboutians had a much easier life. For much of her career, geologist Françoise Goss has been studying this evidence. Shells from freshwater creatures that lived about 9,000 years ago. Shells that tell her Djibouti's landscape used to look very different.
These shells indicate that there was a lake here. And the center of the basin is very far from here and very deep in comparison with this point. So the lake was huge at that time, at the time of these deposits.
In fact, shells like these are found today throughout the Sahara Desert. Evidence the entire region was dotted with deep freshwater lakes in former times. To Françoise Goss, the lakes and shells have only one explanation.
Huge change in rainfall, and this reflects, obviously, a very important change in the climate during the last thousands of years.
This ancient wet climate allowed Djiboutians to lead an entirely different kind of life than that of today's nomads. Just a few hundred yards away from the shell site lie the remains of an old village. Strewn about are hundreds of heavy stone grinding mills, evidence that people were once settled here, that they probably had plenty of rain for their crops. Archaeologist Mohamed Guedda.
There's a strong possibility that the people who occupied this site were sedentary. They used these mills to grind grain and fish meal.
Nearby in the Djibouti highlands, it's clear people weren't the only ones to benefit from a wetter climate. Rock drawings dated to that period show that the elephant, giraffe, deer, rhinoceros, and hippopotamus all thrived here. The same animals that can only be seen where it's wet today, 1,000 miles to the south. It's only recently that scientists have come up with an explanation that can account for such a dramatic difference in climate. The Earth spins on a tilted axis, and we get seasons depending on where that axis is pointing. Here, it's winter in the north, with the axis pointing away from the sun. And here, it's summer. Today's summer actually occurs when the Earth is farthest from the sun in its elliptical orbit. But the Earth's axis wobbles very slowly, cycling every 22,000 years. So 11,000 years ago, the axis was pointing the other way, placing summer on the opposite side of the orbit, where the Earth is closest to the sun, making summers extra hot. The extra heat generated strong winds that sucked moist air in from the ocean, creating monsoon rains that made the entire Sahara wet. These monsoons lasted for several thousand years, but then disappeared as the Earth's axis continued to wobble. In Djibouti, the impact was dramatic.
The lake fell rather rapidly from between 6,000 to about 3,000 years ago. And so because the lake was decreasing and decreasing, and the place where people was living became dry, they were obliged to leave their village and to adapt their life to a new style and to be nomadic.
A change that takes 3,000 years may be rapid to a geologist. But in fact, it gave the people and animals throughout the Sahara plenty of time to adjust. The monsoon cycle is a good example of slow, natural climate change, in contrast to the rapid man-made change expected from greenhouse warming. But that's not the only reason we told this story. Climatologist John Kutzbach has been able to use the Saharan monsoons to test the validity of the climate model here at the National Center for Atmospheric Research. The idea was simple. Tell the computer what was different about the Earth 9,000 years ago and see if it would predict the ancient monsoons.
We know that the glaciers of the Earth were in about the same positions. We know that the carbon dioxide content of the Earth's atmosphere was at pre-industrial revolution values. The main thing that was different 9,000 years ago was the position of the Earth's orbit. And so we had to put those instructions into the computer.
It was like asking the computer what the world would be like in the future. Only in this case, Kutzbach already knew the answer. If the computer predicted a rainy Africa, it would mean it understood the Earth's climate system pretty well. After 400 hours of calculations, the temperature, wind, and rainfall data began to arrive, and they were right on target.
The simulation showed that there was significant increase in rainfall in this entire region of Africa, circled in red here. This was associated with stronger monsoon winds. When we finished this experiment, we were excited to notice that this area corresponds closely with regions that now have small lakes and then had large lakes, and with regions with no lakes today that had very big lakes at that time.
Kutzbach's success and many others like it made climatologists feel their computer models should be taken seriously. While these models may not be perfect, they're our best hope for understanding the future. And as we'll see in our next section, if we let the predictions come true, the cost to people and nature could be horrendous. For the world is a lot more dependent on today's climate, as we'll see next. By the year 2050, computer climate models say the sea level will rise significantly. The basic reason is simple. Steve Schneider.
If you increase the temperature of the planet by, say, 4 or 5 degrees, that's going to do the same thing to the oceans that heating a fluid in a thermometer does. If you heat a fluid, it rises, it expands and rises up, and it's constrained by the thermometer. Well, if you heat the oceans, it's going to expand, and it's constrained by the walls of the continent, so we're going to get sea level rise.
What's more, melting water from the polar ice caps could push the level up even further. Almost every country in the world could lose valuable coastal land. In the United States, that includes Cape Cod, Long Island, Florida, and Louisiana. An entire island nation, the Maldives, could be flooded off the map, creating the world's first greenhouse refugees. The Indonesian islands, with 230 million people and 40% of the world's coastline, could become a nightmare, as would low-lying deltas throughout southern Asia. By the year 2050, most of these areas would still be a couple of feet above sea level, so they wouldn't be permanently flooded. But being just a little higher than the water doesn't count for much. More than anybody else in the world, the people of Holland know what it's like to fight the sea. 2/3 of their country is right around sea level, and the land here stays dry only because of an elaborate system of dikes, which stand guard along the entire 1,000-mile coastline. Towering 30 feet above the high tide mark, these earth and stone dikes seem like overkill, especially when the sea is so calm below. But in 500 years of trying to conquer the sea, the Dutch have learned a hard lesson. Overkill is necessary for one reason only: severe storms. 1953, the coast of Holland. High winds pushed the tide 16 feet above normal, enough to overwhelm the dikes that existed at that time. Frantic efforts were made to stop the sea from surging inland, but its force was too powerful, and the country suffered terribly. Nearly 2,000 people died in this tragedy, and the survivors vowed never to let it happen again. The cost of fulfilling that pledge was staggering. According to Pier Vellinga, Holland's leading authority on dikes and sea level rise.
After the 1953 storm, we had to heighten the dikes by about 2 to 3 meters, and that cost over $10 billion. And that's, well, in the order of 0.5 to 1% of GNP on an annual basis. And, well, that is a continuous amount. It's not just construction, but it's also maintenance, the dunes and the dikes, and it comes back every year.
Constructing dikes is serious business, on the scale of building a first-rate national highway system. Wealthy, developed countries could perhaps afford to follow in Holland's footsteps. But in developing countries like Bangladesh and Indonesia, the expense would be out of reach. Money isn't the only issue either. As well as laborers, thousands of skilled designers and engineers are required to do the job. In countries that don't have these resources, vulnerable coastal towns and cities might have to be abandoned. Either way, building dikes or abandoning valuable land, allowing the sea to rise will mean a tremendous waste.
When the sea level will rise, as we expect now, we must do the same thing again, and it will cost another 10 billion or even more. And, well, technically it's possible, but it's such wrong way of spending money, I would say. We could better invest that in keeping down the rate of climate change.
If we don't keep down the rate of change, humans won't be the only ones to suffer. Take the famous Florida Everglades National Park. Much of this ecosystem depends on its connection to salt water, so walling off the sea makes no sense. But to biologist Larry Harris, the alternative also spells disaster.
If the projections are correct, the sea will come up about 1 foot within the next 25 to 40 years. That means that the edge of the sea that we're standing on today will occur 10 miles north of here by about the year 2010. And if the sea level comes up 2 or 3 feet, then the entire park will be lost. And we fear that Everglades National Park may be one of the first national parks lost from the face of the earth.
At stake here is a treasure chest of unique and endangered wildlife, including countless species of rare wading birds. The American alligator, the manatee, an ancient aquatic cousin of the elephant, and the Florida panther. They live in a closed-in world, quite unlike the time when the Saharan monsoons disappeared, when people and animals had plenty of room to move. If the park is squeezed smaller by rising water, these animals will be forced up against an insurmountable barrier, which stands between the Everglades and other wetlands lying to the north.
The animal species, of course, would normally be able to move up the peninsula if there weren't human habitation and human blockage. But with all of the interstate highways and the chain link fences and barking dogs and golf courses, the wildlife will be caught between the devil and the deep blue sea.
A completely different problem will plague animals in wild areas away from the coast. In many cases, the plants and trees they depend on for survival only grow under specific regional climate conditions that have been stable for thousands of years. But computer climate predictions show entire temperature and rainfall belts shifting several hundred miles by the middle of the next century. The only way for vegetation to survive is to follow. Plant species can move, up to 0.5 mile a year, as their seeds are blown by the wind or carried by animals. But just as in the Everglades, most wild places are hemmed in by towns, cities, and farms, so there won't be any escape route. Unless we actually pay for massive relocation, forests could end up looking like this as they get marooned in the wrong climate. And of course, the animals depending on these forests would be trapped at the same time. And then there's the entire world's food supply. It's also threatened by rapidly shifting climate patterns. A disturbing example of what high temperature and reduced rainfall can do to food crops was the American drought of 1988. That summer, the grain harvest was devastated by the unusual weather. Because grain dealers still had stockpiles from previous years, which they nearly emptied, consumers hardly suffered at all. But what if there had been another bad harvest the next year, and then the year after that? To Lester Brown, president of the World Watch Institute in Washington, this is a scenario we're likely to face if we let global warming continue.
When stocks are so low, the world becomes very vulnerable to another short harvest. And as we look ahead at the prospect of more and more hot summers like the summer of '88, the future food security of the world is becoming more and more questionable. We could see food security replace military security as the principal preoccupation of many governments in the world during the 1990s.
Food crops are extremely sensitive to weather. It doesn't take a whole summer of heat or drought to reduce yields severely. In the case of corn, for instance, just a few 95-degree days in the middle of the growing season can ruin the harvest. For corn to develop, pollen must fall from the top of the plant onto the silks below. Each silk corresponds to one potential kernel on the ear of corn. Silks that fail to catch pollen usually result in missing kernels. Here's the problem. If the temperature hits 95 degrees, the leaves of the corn plant curl up to conserve water, covering the silks. Now, when the pollen drops, many silks won't get any. Worse yet, if there's a hot spell a little earlier, the silks won't grow, but the pollen will. So they can end up missing each other altogether.
When that happens, you can get a severely reduced corn harvest. Corn is important because it accounts for 2/3 of the U.S. grain harvest and 1/8 of the world grain harvest. When the U.S. corn crop is sharply reduced as it was in the summer of 1988, the entire world feels it.
If climate gets consistently warmer, corn production might have to shift to Canada, without American farmers, of course. But that's easier said than done. One of the factors making America's corn belt so productive is deep, rich soils, and the thin soils of Canada aren't nearly as good. Growing the same amount of corn there would cost much more, if it were possible at all. It's true, some agricultural zones might benefit from global warming. For instance, much of the best land in the Soviet Union is underused today because the weather's too cold. But there are many more regions where agriculture would probably suffer, like Southern Asia, where coastal rice production could be ruined by salt water flooding from the sea. In effect, we'll be playing roulette with our food supply if we allow the climate to change.
The evolution of agriculture, reaching its current level of productivity to the point where it will support 5.2 billion people, is closely keyed to the existing climate system. We have no guarantee that if that climate system changes, we'll be able to feed 5.2 billion people as we do today.
To make matters worse, there will be around 10 billion people to feed by the year 2050, if the world's population continues to grow at its present rate. This would create twice the demand for food at the same time supplies are threatened. In a greenhouse future, other vital resources we depend on, like water, may no longer be available where we're accustomed to having them. Will we be prepared to deal with the consequences? What, for instance, would we do if the water coming down this river suddenly slowed to a trickle? This is the mighty Colorado, a legendary blue streak running through one of nature's wonders of the world, the Grand Canyon. And this is a man-made canal carrying some of the Colorado's water through the desert of Arizona. It's part of the Central Arizona Project, built at a cost of $4 billion to supply the growing water needs of the state's largest cities, including Phoenix. Like most users of the Colorado, the residents of Phoenix regard their water as something that will always be there. It's almost beyond imagination to think that global warming could take a lot of that water away by the middle of the next century. Just on the outskirts of the city, there's a grim reminder of what much of Phoenix and the entire Southwest would look like if it weren't for the water from the Colorado. Peter Glick.
The Colorado River is the lifeblood of the Southwest. By most standards, it's not a very big river, but it's just about the only water in the southwestern part of the U.S. The Colorado River is used for power. It's used for irrigation water in the United States and Mexico. It's used for drinking water in Phoenix and Los Angeles and San Diego.
Peter Glick is a leading authority on the world's water resources and on the threat to those resources posed by global warming. Today, he's at Lee's Ferry, Arizona, working with the federal agency that keeps track of how much water is flowing down the Colorado. Official measurements have been taken here ever since 1922, when the river's water was allocated among the various users. Today, every last drop is spoken for, so precise readings are crucial. The amount of water passing by is calculated from the rate at which the propeller blade spins. If this propeller ever slows down, the users of the Colorado will be in trouble.
0.2, 30 and 46 seconds. 30 revolutions, 46 seconds. Right.
Global warming could permanently slow down that propeller blade. That's because the small streams which feed the Colorado come mainly from the Rocky Mountains, where some climate models predict a decrease in snowfall. On top of that, even if the temperature rises only a couple of degrees, the many reservoirs along the river would lose huge amounts of water from additional evaporation. To make matters worse, higher temperatures would also increase demand. All this would mean some hard choices.
If there are decreases in flow in the Colorado, we have to decide who's going to get cut off. Arizona in particular is fairly low in the pecking order, and California is fairly high. We've also promised water to Mexico as part of their allocation of the Colorado. They are at the very end of the river. Do we short Mexico? Do we give Mexico a little bit less water so that we can continue giving U.S. users their share? Do we short U.S. users and give Mexico their full share?
The same hard choices might have to be made for major rivers worldwide that are also being used to capacity. Many flow through several countries, and this could be a prescription for disaster. The Nile, for instance, crosses Ethiopia and Sudan, then flows to the sea through Egypt.
Egypt has already said that it's willing to go to war over the Nile River. Just like the Colorado is the lifeblood of the Southwest, the Nile is the lifeblood of Egypt. There's no other water there.
Rapid change to ecological systems we now depend on. That's the threat of global warming. Having to find new places to grow crops, or new crops to grow where old ones won't. Having to protect thousands of miles of coastline, or relocate millions of people. Having to cope with a change of climate that's coming much faster than any other climate change before. Steve Schneider.
15,000 years ago, the Ice Age began to break up. There was ice sheets literally a mile high over New York City, across through the Great Lakes, over most of northeastern Canada and parts of Europe. And over the next 10,000 years, the ice disappeared. Sea levels rose 100 meters, 300 feet or so. Forests moved thousands of kilometers. Literally, the ecological face of the planet was revamped. It took 10,000 years to warm the planet up only 5 degrees Celsius, about 9 degrees Fahrenheit. And we're talking now about change on that magnitude in a century. So we could be modifying the climate and the whole Earth's environmental system at a rate something between 10 and 100 times faster than nature. And that's guaranteed to have nasty ecological surprises.
The sense of urgency Schneider and other climatologists feel is largely based on their computer models. Yet it's possible these models are too pessimistic, because they can't handle some factors which could dramatically alter the pace of change. University of Chicago climatologist V.L. Ramanathan recently jumped into the middle of a controversy when he asked, what could happen as the oceans get warmer?
As the oceans warm with the rest of the planet, the moisture evaporated from the ocean will increase, just like you see the vapor coming out of this hot coffee cup. Now, what happens to this vapor as it rises into the atmosphere? It can form clouds, just like you see clouds forming on this cold glass.
Clouds influence the Earth's temperature in two opposing ways. On one hand, they reflect sunlight back into space, shading the Earth's surface and cooling the planet. The thicker a cloud is, the greater its cooling effect. On the other hand, clouds create their own version of a greenhouse effect. They form a blanket over the Earth which traps heat. The higher a cloud is, the more heat it traps.
There's a lot of clouds right over the Indonesian monsoon region, where we saw a lot of...
Using computers and satellite data, Ramanathan has determined that on average, clouds today cool the Earth more than they warm it. On this basis, many skeptics suggest extra clouds will stop the world's temperature from rising. But Ramanathan says it's more complicated than that.
If this increased cloudiness is going to be low, thick clouds, that can have a cooling effect and sort of counteract the greenhouse warming of these pollutants. If, on the other hand, this increased cloudiness is going to be upper level but thin clouds, they can trap enormously more heat radiation and sort of amplify the greenhouse warming, which I consider as a very disturbing but plausible scenario. The fundamental issue is any combination of the cloud systems can form, so in a sense the future of the planet relies on how the cloud distribution is going to adjust to the heating of the ocean.
So the impact of extra clouds could go either way. But now consider another complicating factor that can't do anything but make the situation worse. Buried just beneath the floor of the Arctic Ocean, and also beneath the Arctic tundra, are vast quantities of a substance that could cause the world's temperature to rise much faster than the models are projecting. The substance? Methane hydrate, a combination of methane gas and frozen water. It may look like a snowball, but this is 90% methane, a potent greenhouse gas. If global warming thaws the tundra and warms the oceans sufficiently, huge amounts of this gas could be released. There are many other complicating factors like these. They could make things better or worse. Climatologist Steve Schneider.
It might not be 3 degrees warming that we're looking at. It might be only 1 or 2. But if there's a 50% chance that we're going to be less than we think, there's also a 50% chance it's more. Maybe it's going to be 3 to 6. So what we're really doing is we're taking a coin and flipping it. And on one face it says moderate climate change. The other face it says unprecedentedly large climate change. And in my value system, that's not the kind of gamble I like for the planet.
Over 20 billion tons of carbon dioxide and other greenhouse gases now go into the atmosphere every year, a rate which has been growing steadily for the past 2 centuries. Eliminating these emissions fast enough to avoid climate change may be impossible, but that's no reason for inaction. The more we can cut, the less warming there'll be.
2 degrees warming is not nearly as bad as 5 degrees. And if it happens in 50 years, that's much worse than if it happens in 150 years. We can make a substantial difference in the rate of change, and it's the rate of change that is difficult for ecosystems to adapt to and for people to adapt to.
The biggest opportunity for cutting greenhouse gases lies with countries that emit the most. Together, North America and Western Europe, with about 10% of the world's population, produce about 40% of all greenhouse gases. Here, the choices of individual citizens can really make a difference. In the United States, for example, switching to cars that get 50 miles a gallon, double the current average, would cut U.S. greenhouse gases by 3%. Lester Brown.
The real question now is not how large a car that you and I can afford, but what the planet can afford. And the answer is the planet cannot afford very many gas-guzzling automobiles. Or if we're buying a house, how much insulation does it have? And if we were to insulate it better, not only how much would we save on the heating bill, but how much would we save on carbon dioxide emissions?
If all U.S. homes were well insulated, that's another 2% reduction in the nation's greenhouse emissions. Some solutions go beyond individuals. Today, the prices of coal, oil, and gas are misleadingly low because they don't include the potential cost of damage from global warming. But adding in this cost through a tax on fossil fuels would encourage conservation and also give an economic advantage to alternative fuels which don't harm the atmosphere. Generating a fifth of U.S. electricity with alternatives would reduce the nation's greenhouse gases by another 6%. Then there are CFCs. They cause a quarter of the world's greenhouse gas problem today. So until production stops, we should prevent them from escaping into the atmosphere. Venting CFCs, for instance, is still common practice in the servicing of auto air conditioners. But laws requiring recycling of CFCs could cut the country's greenhouse gases by another 2%. Planting forests could also help. New trees grow by taking carbon dioxide out of the atmosphere. So long as these forests are left alone, this carbon dioxide will never go back into the air. If the United States can plant an area about the size of Delaware, less than 1/1000th of the country's land, that would soak up yet another 2% of the nation's carbon dioxide emissions. These 5 measures alone, 5 solutions among dozens possible, already add up to a 15% reduction for the nation.
There's no magic single thing to do. We need to reforest. We need to use energy more efficiently. We need to develop alternatives. We need to shape our lifestyle so we take one trip with multiple errands rather than multiple trips. Every one of these things are nickels and dimes, if you will, but if you nickel and dime long enough, pretty soon you get to half a dollar, you've got the problem half solved.
The world's developing nations also have an important role. So far, countries like China, Brazil, and India haven't caused much of the greenhouse problem. But as these huge nations strive to achieve modern standards of living, their energy use will skyrocket, and the increased greenhouse gas emissions could overwhelm reductions made elsewhere. The only way they can avoid this is by not adopting the same wasteful technologies which were used to build today's industrial countries, and that will require financial aid. As well, they'll need to control population growth. At current birth rates, the population of all developing countries combined will increase by nearly 4 billion over the next half-century. So many additional people will make the job of cutting the world's greenhouse gases even harder. Challenges like these will surely put world leaders in uncharted waters, creating the need for unprecedented levels of international cooperation. But the alternative to bold solutions will be a climate change that's catastrophic.
I'm very concerned because this is not a trivial change in the climate. This is going to cause, for me and my children and my grandchildren, enormous changes in their lifestyles. And I'll be gone, I won't be here, but they will have to deal with it.
What we now have to think about is how we can all become environmentally active, because we all have a stake in the future. We all have a stake in the future habitability of the planet.
If we're not willing to slow the rate of climate change or to stop climate change at all, we'd better be willing to deal with the impacts that climate change is going to bring. The changes in water resources, the changes in agricultural productivity, the changes in sea level. It's one or the other.
There's no doubt that the threat to the global atmosphere is the biggest environmental challenge we face. And yet, it's a threat with a wonderful silver lining, because we're all literally in this together, and we're all going to have to work together to solve it. There are signs that that's beginning to happen already, something we'll look at in the final program of this series. Please join me next time for Race to Save the Planet.
Major funding for Race to Save the Planet is provided by the Annenberg CPB Project and public television viewers. Corporate funding is provided by Ocean Spray. Our continuing aim is to preserve and protect what we cannot create. Additional funding is provided by Jessie Smith Noyes Foundation, Corporation for Public Broadcasting, the John D. and Catherine T. MacArthur Foundation, and Carnegie Corporation of New York, and by the following. For more information on the college telecourse, video cassettes, off-air videotaping, and books based on the series, call 1-800-LEARNER.
This is PBS.
The Global Ecology Handbook, published by Beacon Press, is available for $16.95 plus shipping. A transcript of this program is available for $5. Please call 1-800-TALK-SHOW or send a check to Race to Save the Planet, Journal Graphics, 267 Broadway, New York, New York, 10007. Next on Race to Save the Planet, the modern world, the consumer lifestyle. But the environment pays a price, like the smog-filled air of Los Angeles and the polluted waters of the Rhine River. Watch, do we really want to live this way? Next time on Race to Save the Planet.